Have you ever noticed how a straw in a glass of water appears bent or broken? Or why a fish in a pond isn't exactly where it seems to be? These curious sights are all thanks to a phenomenon called refraction. Refraction is simply the bending of light when it passes from one transparent medium to another, say, from air into water, because its speed changes. When light moves from a rarer medium like air to a denser medium like glass, it slows down and bends towards the normal. And when it goes from a denser to a rarer medium, it speeds up and bends away from the normal. This bending happens at the boundary between the two media, and how much it bends depends on something called the refractive index. Without refraction, we wouldn't have magnifying glasses, eyeglasses, or even cameras. It's a fascinating bridge between the physics of light and the magic we see in daily life. Like most things in physics, refraction follows precise rules known as Snell's laws of refraction. The first law says the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. The second law, famously called Snell's law, says the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for the same pair of media. In equation form, that's sine I divided by sine r equals mu, where mu is the refractive index. This constant tells us how much the light will bend. The higher the mu, the greater the bending. And we can check this experimentally by shining a ray of light through a rectangular glass block and measuring the angles. Nature's precision never fails to impress. The refractive index isn't just about angles, it's also about speed. We can define it as mu equals c divided by v, where c is the speed of light in vacuum and v is the speed of light in the medium. Because light always slows down in denser materials, mu is always greater than 1. For example, in glass, mu is about 1.5, meaning light travels 1.5 times slower in glass than in vacuum. If we know the refractive index, we can easily calculate the speed of light in any medium. This is vital in designing things like optical fibers, which depend on precise control of light speed to carry internet data at breathtaking rates. Light has a neat little trick. It obeys the principle of reversibility. This means that if light can travel from medium A to medium B along a certain path, it can also travel back from B to A along exactly the same path. In a rectangular glass block, this principle ensures that the angle at which the light enters equals the angle at which it finally emerges. It's true for both reflection and refraction, and it's the reason optical instruments can be aligned with such high precision. Next time you see a laser beam passing through a transparent block and coming out parallel to where it went in, remember, reversibility is at work. When light enters a rectangular glass block, it bends towards the normal as it moves from air to glass. Then, as it exits from glass back into air, it bends away from the normal. The result is fascinating. The emergent ray runs parallel to the incident ray, but it's shifted sideways. This sideways shift is called lateral displacement. The amount of lateral displacement depends on the block's thickness, the angle of incidence, and the refractive index. Also, different colors of light bend by different amounts. Violet light bends more than red light because it has a slightly higher refractive index. Let's apply this in a calculation. Suppose we have a glass block of thickness 3 cm with an angle of incidence of 45 degrees and a refractive index of 1.5. Step 1. We use Snell's law, sine r equals sine I divided by mu. That's sine 45 degrees divided by 1.5. This gives us the refracted angle r. Step 2. We plug it into the lateral displacement formula, d equals t times sine of I minus r divided by cosine r, where t is the thickness. Substituting the values, we get lateral displacement d is approximately 0.99 cm. Let's quickly recap. Refraction is the bending of light caused by a change in speed as it moves between different media. Snell's laws give us the precise relationship between incident and refracted angles, and refractive index links this bending to light's speed. The principle of reversibility assures predictable light paths, and phenomena like lateral displacement show how refraction affects ray positioning. These principles are not just textbook physics, they're the foundation of cameras, microscopes, fiber optics, and even the way our eyes see. I hope this session has made you see, quite literally, how light's journey is shaped by the world around it. In our next session, we'll dive into another fascinating property of light. See you there.